The goal of this lab is to find the internal resistance of a battery, and to do that, we first have to know how to set up a simple circuit that enables you to determine the internal resistance of a battery, including proper placement of meters. So to do that, we're using this FET simulation. I'm going to put a battery here and a resistor here, and using these two and connecting these two using wires, I'm gonna make a simple circuit, and through that I'm gonna find the internal resistance. But since this battery has to be like a real life battery, and all real life batteries have internal resistance, I'm gonna press this button and give it 2 ohms of resistance. If this battery does not have internal resistance, then this battery would just be an ideal one, and it wouldn't yield an experimental result. So I'm gonna put it like that, and for the voltage, I'm gonna keep it at 30, and that's done. For resistance, I'm gonna first put it at 0, but through the experiment, I'm gonna increase the resistance in order to continuously change the value of current. So now that these two are ready, I'm gonna connect these two with wires. And when these two are connected, we have a complete simple circuit. Although we have a simple complete circuit, but we still don't have meters to measure appropriate values of variables, so we're going to have to use these meters to do that. And in this experiment, I'm going to use a voltmeter and an ammeter to measure the values. So the reason I'm going to use voltmeters to measure the value of VAB, which basically is terminal voltage, and that is the potential difference between points A and B, and points A and B must have a battery between them. So I'm going to put one here, I'm going to put one there, and the value here would give us the value of terminal voltage. To add on to that, if like this, if the battery does not have internal resistance, then the value of terminal voltage would equal the value of EMF, simply because there's no resistance within the battery. And I have this ammeter to measure the value of current. Now these two are ready, and this is how you set up a simple circuit that enables you to determine the internal resistance. Now we have made a circuit that we can use to find the internal resistance. And now we have to know how to collect and analyze graphical data for a real battery, which also means a battery with internal resistance, to determine the value of the internal resistance and the EMF of the battery from the graph. So before we draw the graph, we first have to know the equation. And the equation states that the terminal voltage, VAB, is equal to EMF subtracted by current multiplied by internal resistance. So VAB equals EMF minus IR. So since we have to find the value of EMF and R from the graph, we're gonna set I, which is current, as the independent variable, and VAB, the terminal voltage, as the dependent variable. In other words, we're gonna continuously change the value of current, and we're gonna measure the value of terminal voltage to create the graph and find the values of EMF and R. So independent variable will be current, and the short name will be I, and the unit is this, and now we have this. And for y-axis, we're going to put our dependent variable, which is terminal voltage. and string will be VAB, and this will be just volts. Now we have x-axis and y-axis. We're going to start collecting data from our created circuit. So I mentioned it earlier that I have put the resistance value, the value of resistance as 0 in the first place. But to collect data, we're going to first put it at 1, and we're going to increase it by 1 every time we measure and record the data. So let's put it at 1. Now, if we see the values given, the value of current is 10, and the value of voltage is also 10. Now we're going to increase it by 1 again, and the value of current is 7.5 now, and the value of voltage is 15. If we increase it by 3, we get 6, and we get 18. And if we continue this, we get this graph. Sorry, get this graph. So I made this earlier to save time, so our video does not exceed 10 minutes. But this is how the graph looks like when all data is collected. So as we saw before, 10, 10, 7.5, 15, 6, 18. The values are equal. And if you see that it's a linear graph, a negative linear graph, and it says the slope is -2 and the y-intercept is 30. If you focus on the equation that we talked about at the start of the video, which is VAB equals EMF minus IR, since I is the x variable in this graph, we know that -r is the slope and EMF is the y-intercept. So you can simply think of this as a linear graph. Y equals mx plus c, and m would be -r and c would be EMF. And since the slope on this graph says it's -2, we know that -r is equal to -2, and if we cancel out the negative signs, we know that r is equal to 2. Also, on this graph it says the b, which is the y-intercept, is 30, and since we know that EMF is equal to y-intercept, we know that EMF is equal to 30, and we know that EMF is equal to 30 volts. And as we said earlier, R is a symbol of internal resistance, and from this we also know that the value of internal resistance is 2. Now, to prove that this graph is correct and that we can actually find the value of internal resistance and EMF from the graph, we can compare these calculated value with this value here. So when I made this circuit, I put the internal resistance as 2 ohms, and it's giving me 2, the value 2. So we know that they're equal and they're correct. And since we set up the voltage of the battery as 30 volts, and it's giving me 30, the exact same value, we can conclude that we can collect and analyze graphical data for a real-life battery to determine the value of the internal resistance and the EMF of the battery from the graph. Finally, we should know how to incorporate Kirchhoff's loop rule into analysis, and the rule states that the sum of all the electric potential differences around a loop is equal to 0. And we can prove this rule in this experiment by doing a simple calculation of V equals IR. Since we know that the voltage is 30 volts, which is shown here, we know that 30 equals IR, and we know that when the external resistance is 3, we know that the total resistance is 3 plus 2, since it's a loop. It's just simply an addition, so 3 plus 2 is 5. So we know that I should equal to 6. If we look at our graph, when our external resistance is 3 ohms, we know that the current is 6. So that's how we can prove the loop rule. And this is why we can incorporate the loop rule into our analysis.